All right, so do you guys have any on 6.1 or on 6.2a that you have questions on that you want to look through up here? Unfortunately, we don't have time for an all of them situation. I will get answer keys start popping up now that we've got some homework coming in. I will post answer keys as we get things that are, graded and finished. But any specific questions on 6.1 or 6.2a? Yeah. Let's look at 17 on 6.2. Which one is that? Cool. So yeah, we did one very much like this yesterday. What they give us on 17 for 6.2a, looking at number 17, we were given the sine of theta is 3/5. When we get one like this, I highly recommend giving yourself a triangle. It's so much easier to see these if we have a triangle, because we were asked to find all 6 trig functions for theta. So I'm going to give us a triangle. I'm going to draw it this way just because I can. Here's my right angle. I'm going to call this guy theta. I'm just picking a random one of the other angles. So sine is made up of which 2 pieces? Opposite on hypotenuse. So we're on opposite over hypotenuse. So if we're looking at this triangle over here, it does that sometimes. It's grumpy and likes to play games. So yes, if it ever really does go away, please let me know. It should usually pop back, but not always. So this side next to my theta, that's my adjacent side. This guy across from my angle is, of course, the opposite side because it's opposite. It's directly across from the angle. And
interruption. Students that are testing their period may be dismissed to their testing room. Thank you.
And our adjacent, not adjacent, that's what happens when I think and write at the same time. Our hypotenuse is over here. Okay? So, I say it should be an email in your 500 mail account, or I can pull up the list if you need me to look it up for you. Okay. So you'll get an email if you need to. So our opposite side should have a measurement of 3. Our hypotenuse gets the 5. And how could I figure out what the other side is? Pythagorean theorem. We take our 3 squared plus whatever our adjacent side is. I'm just going to call it a because it's adjacent, and why not? Equals our hypotenuse squared, 5 squared. So 3 squared gives us 9 plus our a squared.
Is that a Pythagorean? Yeah. Is that 3, 4, 5?
It is a 3, 4, 5, yes. It's one of those kind of like standard triangles, but if you don't notice that, this is the way you can find it. Because yes, if we notice the 3 and the 5, we were like, oh, it's a 3, 4, 5 triangle, good to go, rock on. You don't have to do the Pythagorean theorem for it. But some of us won't notice that, and that's okay. So this would be how you get there. So our a squared gives us 16, because we subtract 9 from both sides, which gives us an a of 4. So we get exactly to that 3, 4, 5 special triangle. So once we get there, we can do all 6 of our trig functions, where we have our sine being our opposite over hypotenuse. So opposite over hypotenuse, our opposite sine was 3, our hypotenuse is 5. So we get 3/5. Again, that's exactly what they gave us. Great opportunity to check it, or you can just say, well, I know sine is right there. Our cosine is what? Adjacent over hypotenuse. So what's our value here? 4/5, or 4 over 5. And so our tangent is what? Mm-hmm. Opposite over adjacent, so 3 over 4. Then we'll do our reciprocal pieces. So sine goes with cosecant. So what is cosecant? 5/3. They're reciprocals of each other. Let's flip them. So secant is what? 5/4. And cotangent is what? 4/3. Okay? So once we get our feet underneath us on these, they're not too awful. They're just really scary looking going into it. What's that?
Number 11.
Number 11 on the same one?
Yeah.
On 6-2? Okay. Cool. I'm going to go to the right. You said 11?
Yeah.
Okay, cool. Just double checking because I didn't write it down and then I moved things and I'm like, oh, my brain lost. All right, so on 11, we are given a triangle. It looks like this. We have a right triangle. They give us that this side is x, this side is 4, this side is y, and that this angle here is 30 degrees. So we worked with a triangle very similar to this yesterday that had really random sides on it. So if I know this is 90 and this is 30, what's this angle? 60. This is a 30, 60, 90 triangle. And we're trying to figure out what these two sides are. When we did them yesterday and we were looking at them, we looked at our 30, 60, 90 in terms of a equilateral, right? So 30, 60, 90 is related to equilaterals, which means this whole side is 8. Which means which letter does that help me find? It helps me find x for sure. Because I know that this bottom side is 4, so this height has to be twice it. So this x is going to be 8. 30, 60, 90 triangles are always kind of based off of a half of an equilateral triangle. We did that one yesterday. So I know that this little side is 4, which means if we look at our big equilateral triangle, the whole side is 8. So that means this side, since it's an equilateral triangle, is 8. Okay? Now I have a leg. I have my hypotenuse. Can I use that to find the height here? You can do a Pythagorean theorem. You could pull up our 30, 60, 90 from yesterday and do our x square root of 3, which would be what our thing is. But you're going to get a radical. It's going to be kind of icky, and that's okay. But that's how we can find it on these 30, 60, 90s. Think about it as our half of an equilateral triangle, and that gives us our relationship to the sides. It's not going to be a thing we do tons after 6-2A. Like, for the most part, we're going to be working with these guys over here, but just trying to get us to see the connection in the pieces here. That's what they're trying to get us to do. And we don't have to do anything else. We don't have to do sine, cosine for it. We're just finding what x is, finding what y is. Okay? I've gotten a lot of questions about 1 cycle 11. I've gotten a lot of questions about it. Okay, that's kind of why we have the question cards today. So I've had a lot of questions from a lot of different people on those. Okay, because when we're going on to 6-2B, it's going to feel like a big old change in direction because we're not going to have like triangles all that much. A little bit, but mostly not. So the reason we have 6-2A, 6-2B, 6-2C is because section 6-2 covers, holy cow, way too dang much. Like, there is a lot in section 6-2. So that's why we have it busted up like this, because 6-2A really focuses kind of on the triangles, and 6-2B and 6-2C are really similar, but they're both very long. So that's why we've got it busted up. We're going to be in 6-2 pretty much the rest of this week. Like, this, holy cow, covers way too much in one section. Okay. So, you ready to go on to the next part? Cool. I just wanted us to kind of have a little check-in on that because I know that was becoming a sticking point for some of us, and I didn't want us to get totally stuck in the triangle zone and without being able to move on. So we're going to work with some things called fundamental trig identities These are going to be things, some of which you will already know, some of it you will not, and we will need to memorize them. Mostly it's going to be these guys that you will not have seen before, our Pythagorean IDs. So our reciprocal identities, those are the things we've been talking about a lot, where our sine goes with cosecant and our secant goes with cosine and cotangent goes with tangent. So, make sure I've got this set to full page. There we go. That way I can zoom in to right and you can still see the whole thing. So when we're talking about our reciprocal IDs, or reciprocal identities, that's when we're thinking about cosecant of theta being the same thing as 1 over sine of theta. They're related to each other. They are partners, they are buddies. Secant of theta is the same thing as 1 over cosine theta. We did that again with the numbers. They're parts of each other. And that our cotangent of theta is 1 over tangent of theta. So they're all pieces of each other. And again, those ones we've talked through before, but like, I like to kind of state it several times when we have something kind of new and weird. For tangent and cotangent identities, what we're doing is we're looking at relating tangent to sine and cosine, and cotangent to sine and cosine. So when we're thinking about tangent of theta, there's another way I could write that. It's the same thing as if I had sine of theta over cosine theta. I'm going to move that one over just a smidge, just so we don't run out of space for Pythagorean IDs. And then I'm going to give us a little bit of a barrier here, just so we're really clear where things are switching. Like that. There we go. And we can do the same thing with cotangent. We can write that in terms of sine and cosine, but remember it's a reciprocal of tangent. So not cosine, cotangent, sorry. Cotangent is the same thing as cosine theta over sine theta. And then our last piece here is going to be, whoop, wrong page, our Pythagorean identities. These are going to be things you're going to need to memorize. We are going to use these bunches and bunches and bunches for like the rest of the class. Like, we'll use these a lot. And they're a little bit weird. So our first one says sine squared of theta plus cosine squared theta equals 1. Well, we have two more. 1 plus tangent squared of theta equals secant squared theta. And then our last Pythagorean identity is 1 plus cotangent squared is cosecant squared. And these are all like based off each other, and we're gonna see that here in a little bit. We're gonna look through verifying these and seeing what's happening here and why, because right now it's just kind of like magic. When we write trig functions with a power, we typically put it inside, like not outside the angle, because we don't want you to think of it being sine of 90 squared, like as an angle. We want sine squared, like the sine that's being squared, not the angle that's being squared. So that's why when we write our powers, we put them inside here. It's not that we're squaring the angle. We're taking our sine, our 3/5, whatever. That piece is the thing that's been squared. So sine, like if I write it as sine squared theta is the same thing as sine of theta as a group squared, not the angle. We're not squaring the angle, we're squaring the sine. So it means the same thing, it's just this is the way we typically write it because we're trying to write with as few parentheses as possible because we like things simplified. So these are things we're going to need to know. And we're going to use them often enough that we should know them backwards, forwards, upside down, inside out. Like, we're going to use them a lot. These are things that come up every math class you take after this that uses trig will use the Pythagorean identities. These are one of those, like, constants moving forward in every trig class that you use. Okay, so these are super duper important pieces, so make sure you get these written down. Super duper duper, duper 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 important. Because what we're going to work with now is we're going to be living in these words. We're not going to do so much with triangles for a little while. And we're going to deal with kind of verifying, solving, and proving things using the words. So our first couple that we're going to do is we're actually going to prove these ones and see what's happening and look at why we have them and why we care and what's going on. So, let's see. I don't see anybody still writing, so I'm going to change it. If you need me to go back at any point, please let me know. So we're going to be proving tangent, and we're going to do all of our Pythagorean identities. So what we're doing when we say proving is we're manipulating one side. We're not necessarily crossing the equal sign. When we're verifying, when we're proving, we're not trying to cross the equal sign. I'm trying to manipulate one side to make it match the other side. So we're not crossing the equal sign, just playing with one side. So we want to try and get tangent to equal sine theta over cosine theta. And I could start over here, but this side's already pretty simple. So I'm going to play with this side because it's complicated, and complicated things we can change. So when we're coming in here to verify that tangent theta is the same thing as sine theta over cosine theta, I'm going to manipulate this right-hand side to see if I can get it to be a tangent. So I'm going to take my sine theta over cosine theta, and I'm going to rewrite sine. Sine is made up of which two pieces of our triangle again? Yeah. Our sine is our opposite over hypotenuse, right? Opposite over hypotenuse. And cosine is which piece? Adjacent over hypotenuse. Okay, so I didn't change what these things were. I just changed how they were written, right? When I have a fraction divided by a fraction, we look at that and we go, bleh. Keep, change, flip, take the top and multiply by the reciprocal of the bottom, whatever words you use to think it through. So I'm going to make this be our opposite over hypotenuse times reciprocal of the bottom, hypotenuse over adjacent. What happens when we do that? The hypotenuse cancels out. And we're left with opposite over adjacent, which stands for what trig function? That's tangent. TOA. So tangent of theta is the same thing as opposite over adjacent. And I've taken my sine over cosine and made it match this left-hand side where it says tangent of theta. So that's what we mean when we say verifying. I'm not necessarily changing both sides. I want to get one side to match the other. Sometimes we might do a little bit on both sides, but we're going to try and do most things on one side of our equal sign. So this is proving that tangent does in fact equal sine over cosine. This is what it's doing. Okay? We're going to do very similar things over here, verifying our trig identities, our Pythagorean identities. But questions on the first one before we go into the next one? Okay, so like I said, when we have our sine squared theta, that's the same thing as saying the sine of theta as a group being squared. So I can rewrite my sine of theta same way I did on the other one, where I write my sine as the fraction opposite over hypotenuse, right? This is our opposite over hypotenuse. But our whole sine here is being squared. So it's opposite over hypotenuse squared. Plus our cosine squared, which I can write as adjacent over hypotenuse quantity squared equals 1. Right. Well, I'd really like to get everybody out of those parentheses because ew. So I'm going to bring the square in, square each side, top and bottom. So I'm going to rewrite this as a new color. We're going to have our fraction that has, whoa, wrong pen. There we go. Opposite squared over hypotenuse squared plus our adjacent squared over hypotenuse squared. And what do we notice here? What can I do? They have the common denominator, so I can add them together. So we can write this as opposite squared plus adjacent squared over our hypotenuse squared. And we have that currently set as equals to 1. And this is going to be like the only time we actually do cross the equal sign because I want us to see why the heck we call these Pythagorean identities. All right? It's going to be very, very rare that we do this, but we're going to do it on this one. Because I want to get this fraction gone because ew. So I'm going to multiply both sides by our hypotenuse squared. This is, again, just so we can kind of see why this is called a Pythagorean ID. This is our opposite squared plus our adjacent squared equals 1 times hypotenuse squared, so hypotenuse squared. The reason this is called a Pythagorean identity, this is the Pythagorean theorem. This is a side squared plus the other side squared plus the hypotenuse, or equals the hypotenuse squared. So that's why these are called Pythagorean identities. All of them are based off of this. We are not going to do all of them using the words opposite and adjacent because they're going to get super duper gross really, really fast. But this is where it's coming from. So these are all coming based off of those triangles we've been working with. We're just going to like walk away from triangles, but it's all based on triangles. Okay? So that's where these are coming from. So these are called Pythagorean identities because of that. We're mostly going to work with them in this form. Okay? So questions on these two. We're going to do 2 more, our other 2 trig identities, but we're not going to do them using opposite and hypotenuse. We're going to switch things back into sine and cosine. So for the most part, when we're looking at solving, verifying, those kind of things, we're going to be using sine and cosine as kind of our home base. So, I'm not turning my page yet. Looking at here. So we're going to look at our next Pythagorean identity. That's our 1 plus tangent squared equals secant squared. And I'm not going to put them into our opposite, adjacent, hypotenuse stuff. I'm going to put them all in terms of sine and cosine. So we have here our 1 plus the tangent squared of theta equals secant squared theta. So if I want to write this in terms of sine and cosine, we're going to have our 1 plus, and if I write tangent squared in terms of sine and cosine, tangent is made up of sine over cosine. So this is the same thing as having sine squared theta over cosine squared theta. All right, you see that? Because it's weird. And I can make that into 2 or 3 steps if we need more detail. And we want to know if we can make that equal secant squared. Secant is related to which piece? Cosine or sine? Cosine. Secant squared is the same thing as 1 over cosine squared, right? And you can either leave it as secant squared and do the extra step at the bottom, or you can put it here so we know where we're going. I'm totally okay. It's okay if we change both sides a little bit. We're just going to focus mostly on one side. So I'm going to manipulate this side because holy cow, is this side gross. So I would really like to simplify this side. What do I need to do to be able to simplify this side without crossing the equal sign? Yeah, we're going to need to get a common denominator. So I'm going to put my 1 as cosine squared over cosine squared. It's still going to give us 1 cosine squared theta over cosine squared theta. And then we're plus our sine squared theta over cosine squared theta. So we got it to a common denominator. What can we do next? Yeah, put them on the same line. So we're combining our fractions. So we've got our cosine squared theta plus sine squared theta over cosine squared theta. This piece should be a little familiar by now, hopefully. Because this guy, which I'm changing my opacity, there we go. This guy is the one we just did. Cosine squared plus sine squared. And sine squared plus cosine squared, cosine squared plus sine squared, same deal, doesn't matter what order it is. No matter what, that thing equals 1 over cosine squared. That's one of those Pythagorean identities. And that is exactly what we were hoping for when we got down here. If you didn't switch it to cosine squared at the beginning, we would just notice that cosine squared theta would be the exact same thing as, or 1 over cosine squared is the same thing as secant, because 1 over cosine is secant. But this is how we do our verifying. We're going to have a big stretch where we're only looking at one side. It's okay if we do a little manipulation on both sides, but we're going to focus mostly on one side. So this is how we prove this identity. Okay? And this is going to be how we do all of our simplification stuff for the most part in this section. We're going to do most of it using sines and cosines instead of too much opposite adjacent stuff. There might be a little, but it's going to be really rare. More often than not, it's sine versus cosine. Let's do one more trick, our last trig identity. There we go. I'm good with words. So we've got our 1 plus cotangent squared equals cosecant squared. And so again, I'm going to put these all in terms of sine and cosine because that makes it a little bit easier to deal with and manipulate. We're significantly more comfortable with that. So if we have our 1 plus cotangent squared of theta equals cosecant squared theta, I can write this as our 1 plus and cotangent squared. That's the reciprocal of tangent. So that's going to give us cosine squared theta over sine squared theta. And I'm going to get it back to cosecant just to see that we don't have to change it on the right-hand side at all if we don't want to. So what should we do next on this one? I want to be able to combine these together, so let's get to a common denominator. So I'm going to make this 1 be written as sine squared theta over sine squared theta. It still counts as a 1. It's just a weird looking 1. Plus our cosine squared over sine squared. So I took my 1 and put it in terms of sines. Now we've got that common denominator, so we're going to smush them together. Our denominator is now sine squared theta, and our numerator is sine squared theta plus cosine squared theta. So what does our numerator equal? 1. That's, again, that first Pythagorean identity. We will use that one a bunch of times. That one's going to be the one we use most frequently. We will use all of them, but we will use the sine and cosine one the most frequently. So this is the same thing as having 1 over sine squared theta. And when I have 1 over sine, which trig identity does that go to? Or which trig function? So 1 over sine, that is our reciprocal of our cosecant squared theta. And that's exactly what we wanted this to be over here, was cosecant squared. Okay, questions on this one? Because they're kind of weird, but that's where all these trig identities are coming from, kind of verifying and working with them. And I'll show you how we're going to use it more towards the homework here in just a second. But I'm going to give you a second to write these down because I still see a bunch of people writing. I'm going to grab my water, and then we'll look at the first couple of problems. We still got 10 minutes. We're good on time. Love it. To walk all the way, that's why I need my water. All right. So we're going to be given problems that look kind of like this. We don't have equal signs, so we don't really have a goal. We're just going to simplify as much as we can and call it that. So we're not crossing equal signs. We're just trying to simplify this as much as possible. So if I have cosine of x, tangent of x, and technically those are, again, Greek because they're angles, but they just look like x's. They're chi, but x is fine. A lot of times they will use x in there just because we're familiar with x. We're used to it. So I want to put these both in terms of sine and cosine. That makes things a lot easier to kind of deal with and see what's going on. So cosine of x is already in terms of sine and cosine. That's a good buddy. We like cosine. Tangent of x, how do I write tangent in terms of sine and cosine? Sine over cosine. So this is sine of x over cosine of x. What happens? What cancels out? Cosine cancels out. Our cosine of x and cosine of x cancel out. So cosine x times tangent x is going to be the same exact thing as sine of x. So we're just simplifying. We want to get it down to as simplified as we can. And it should always be one of our 6 trig functions. We should be able to get it down as few as possible. So then we're going to do the same kind of thing using our cotangent theta over cosecant theta. So again, I'm going to write these in terms of sine and cosine. So it's cotangent theta divided by cosecant theta. So cotangent What's up? Okay, just making sure. So cotangent, remember that's our reciprocal of tangent. So instead of being sine over cosine, it's cosine theta over sine theta. And cosecant is the reciprocal of sine. So we're 1 over sine of theta. And now I have fractions and fractions, and they're super gross. Ew. So we're going to do where we can take it out of our double fraction, and we're going to have our keep, change, flip, multiply by the reciprocal. However your brain chooses to word that to you is fine. So I'm going to take my numerator and keep it. So we're going to have our cosine theta over sine theta. And we're going to multiply by the reciprocal of the bottom. Keep, change, flip. So it's going to be sine theta over 1. What happens? The signs cancel out here. So this whole thing is going to simplify down to just be cosine of theta. So switching things into sines and cosines will make it a little bit easier. Let's do one more. A little bit bigger. So again, we're using x here. So we've got secant of x times cotangent of x minus sine of x. And we're going to go ahead and simplify as far as we can go, make it as simple as we can get. So I'm going to write these in terms of sines and cosines as our way to get started. So our secant of x, secant is the same thing as 1 over cosine. Cotangent, remember that's our reciprocal of tangent, so it's not sine over x, it's cosine over sine. And then we're subtracting our sine of x. What do we notice first here? Our cosines are going to cancel out over here. So I've got 1 over sine of x minus sine of x. Yeah, let's get to a common denominator. So I need to multiply this piece by sine of x over sine of x in order to get that sign in the denominator. I can multiply by 1. It's a funky looking 1, but it's there. So what we have is our, change the colors, 1 over sine of x minus sine of x times sine of x gives us sine squared x over sine x. Because we want them to have that common denominator so I can push these together. So our denominator is going to be sine of x, and our numerator is 1 minus sine squared of x. I wonder if 1 minus sine squared x is something we can do something with. So I'm going to put up here one of our trig identities that involved a sine squared. If I had sine squared theta plus cosine squared theta equals 1. Is there a way to find a piece that looks like 1 minus sine squared x? If I subtract our sine squared here from both sides, we can rewrite this as our cosine squared is the same thing as 1 minus sine squared, right? So I can rewrite 1 minus sine squared as cosine squared. This is the same thing as having cosine squared theta, oh, x, excuse me, we're an x on this problem, over sine of x. And that's one way to write this simplified. There's one other way we can write this, which is actually to get it back into our 6 trig functions, where I take this and split apart my squared to rewrite my cosine squared as cosine of x times cosine of x over sine of x, right? Those things mean the same thing. Cosine over sine is which of the trig functions? This piece, cosine over sine. It's not cosecant. It's our cotangent. So this is, I could rewrite as cosine of x times our cotangent of x. Okay, so this would be my favorite answer, but this one's not terrible. Okay, yes, dear. Yes. There will be lots and lots and lots of these, and we are going to keep working with them. I'm going to put up the page that has all the information on it, so just don't be afraid. So, let's see that date. I don't think that date's... That date's not right. We're going to do 116 on 6-2. That's 6. 16. There we go. I don't know why I did that in pink instead of white, but I did. All right. All right. Have a great rest of your day. I'll see you tomorrow. Bye. There's a lot of stuff in this one.